Please don't forget to like, subscribe, and comment. Thank you so much.
Join us at Like Learning School and experience a transformative education journey. Visit our website at www.likelearningschool.com or contact us at +2348085095144 to learn more and get started today.
That deformation of solids, Hooke's law and what have you. You can see where I am?
Yeah, I can.
Okay. Do you remember Hooke's law? That's from O level.
F equals to KE.
F equal to KE. What does F stand for?
Force.
K.
Constants.
Spring constant, and then E.
Extension.
Okay, that's the mathematical equation for Hooke's law. F equal to KE. F for load or force. K equal to spring constant. E for extension. But what does Hooke's law talk about? What does it really talk about?
Hooke's law states that the extension of the string is directly proportional to the force applied on it until we have reached its limits of proportionality.
Oh, okay. Yeah, you captured it well. Hooke's law states that extension is directly proportional to the applied force. That is beneath the elastic limit. Because above the elastic limit, it doesn't obey Hooke's law again. So, just a quick review. And please, I'm on the next page, so that I can just note this down. Hooke's law, beneath the elastic limit, extension is proportional to the applied force. Extension is proportional, or directly proportional if you like. Extension E is directly proportional. Some textbook can use X for extension. It doesn't matter. Proportional, directly proportional to the load or force, which is F. Okay, so mathematically, as we rightly said, F is equal to KE. Okay, so if obviously if we plot the graph of F against E or E against F, by the way, what the proper way, based on that definition, which one is the independent variable?
What did you say?
Based on this definition of Hooke's law, which one is the independent variable?
Independent variable.
Yes. Yeah, which one is the independent variable? Is it the extension or the force?
Oh, independent variable, the one that was like equal or force.
Independent, yes, is the force. Okay, dependent is the extension. Of course, K is a spring constant. And you know the unit of K will be, the SI unit should be SI unit of K should be, since it is force, okay, let me just make a solid formula. Or K is equal to F over E, isn't it?
Yeah.
So the unit of K should be Newton per meter. Okay, unit of K is Newton per meter because it's about force over length. All right. Okay. What I was trying to tell you is, if the independent variable is force, the proper way of plotting it, although the other way can be, you can also see it plotted in the other way. But the the reasonable way of plotting it, because the independent variable is usually on the x-axis. So force will be here in Newton, extension will be here in whatever unit you like, maybe meter. Okay, so beneath the elastic limit, as we said, extension is directly proportional to the resultant, to the force. So it's going to look like this. Are you on the Jamboard, please?
Yeah.
All right. And let me draw this again. Beneath the elastic limit is going to be like this. Now, once it goes beyond the elastic limit, it's no longer going to be proportional, so it will curve. This position we can call E is the limit of proportionality, or elastic limit. And you know, A to E is the elastic region. E to any position F is a plastic region. So A to E, you know, is elastic region, just from known to unknown. And E to F is the plastic region. So when you stretch a string and it is still within its elastic limit, and it can return to its original length after releasing the load, after letting the load off. But if once it enters the plastic region, it doesn't return fully to its original length after the load is removed. So we say that it has been permanently deformed. You know what I'm talking about?
Yeah.
Okay, of course, E is the limit of proportional elastic limit. So Hooke's law is obeyed within which region? From where to where is Hooke's law obeyed?
A to E.
A to E, okay. So what will be the slope? What will the slope give you?
The slope would be wait, what do you mean by this?
Yeah, gradient. What would the gradient give you?
The constant.
Of E. Remember, this is a graph of E against F. What would the gradient give you?
The constants.
Yeah, what will be the value? Slope is equal to, since it is E plotted against F, that's going to be E over F. And what would that be? I think that should be 1 over K, isn't it?
Yeah.
Do you agree? Let me write this one lower. This is, just hold on, let me put this here, F in Newton. The slope is going to give us 1 over E. Because 1 over K rather. Because K itself is F over E. So if the slope is E over F, because it is E rise over run. Rise is E, run is F. So E over F will now be 1 over K. That is if you plotted E against F. You know what I'm talking about?
Yeah.
All right. So Hooke's law states that beneath the elastic limit, extension E is directly proportional to the load or force. It is only proportional when it is beneath the elastic limit, but beyond it, it is no longer proportional. So the proportionality is between A to E. If you stretch it beyond the elastic limit, it doesn't return to its original length when released. So if it is stretched still within the elastic limit, the elastic region, it can return to its original length. All right, please, can you go to the previous page? I want to show you something so that we can move on from there. So a graph of F, or extension over F, as we have said, gives a slope of 1 over K. Remember, X stands for extension. We can as well call it extension against F. All of these are extensions against F. extension against F, or F against extension. So extension against F, the slope gives 1 over K, because it is rise that's rise over run, rise over run, which is E over F, that gives 1 over K. But if it is a graph of F over E, F over E, the slope gives directly K, spring constant. Now this is what I'm talking about. Let me zoom it in here properly so that we can see. You know, this initial graph we plotted is E over F, E against F, which gives 1 over K. But if we decide to plot a graph of F over F against E, like this, F here, E here, this one is going to give us, the slope will give us directly spring constant. So this is how it's going to look. But we need to notice something. When a graph of F is plotted against E, after or beyond the elastic limit, the graph will curve downwards like this. So if E is the elastic limit, it's going to curve downwards like this. Take note of the difference. F against E, this is the elastic region. The plastic region is going to curve downward. Compare it with a graph of E against F. A to E is the elastic region. E to F is curving upwards for the plastic region. That is for E against F, extension against load, extension against force. And you can see the difference when it is force against extension. So what I'm saying is, if we take the slope here, this particular one, where we plotted force against extension, the slope will give us rise, which is F, over run, which is E, and that is directly spring constant. Slope is F over E, which is a spring constant K. This gives a spring constant K. Unlike a graph of E against F, the slope or gradient gives E over F, which is 1 over spring constant. Okay. Oh, I should have called this a different name, so that let me call this P instead of F, so it doesn't confuse some of the things that we need to talk about. So A to E is the elastic region. When you stretch it and you remove the load, it will return to its original length. So it has not been permanently deformed. E to P is the plastic region. When you stretch it beyond the elastic region and you remove the load or the force, it will no longer return to its original length, because E is the elastic limit. Beyond the elastic limit, it doesn't obey Hooke's law again. Before the elastic limit or below the elastic limit, it obeys Hooke's law, where extension is directly proportional to force. So it forms a straight line that passes through the origin. Just like if you plot the graph of F against E, it will also produce a straight line that passes through the origin. And after the elastic limit, it curves, because E to P is the plastic region. Alright, but I want us to notice some important features of the graph. I want to review both so that we can compare. Let's see a graph of E plotted against E, F against extension. You see, when we take the slope gives us directly spring constant. And as you can see, the slope for the black one is bigger than the slope for the blue one. That means the spring constant of M, which is the black one, is bigger than the spring constant for Q, which is the blue one, because it is steeper. M is steeper, and the slope gives directly spring constant. Spring constant of M is bigger than spring constant of Q. But I need you to see the difference. When you plot E against F, the slope is not K, but it's 1 over K. So even though B is steeper than A, the black one here is steeper than the red one, the slope of A is actually, or what I mean is, yes, I said even though B is steeper than A, meaning that B has a higher slope than A, but the spring constant of A is bigger than the spring constant of B. The spring constant of A, the red one, is bigger than the spring constant of B, the black one. Reason being that it is the other way around. The graph is plotted the other way around. It is E against F instead of the normal F against E that we usually plot. I just want us to see how we can find the work done or the energy stored in a string. The work done or the energy stored in a string or in a spring within the region where it obeys Hooke's law is the same way we can calculate work done, force times distance moved in the direction of the force. And since we are going to use the average force, so we have half F times that distance. Now this time around, the distance is going to be the extension. So that's going to give us average force times the extension. Work done is force times distance. So it is the average force times the distance. Average in the sense that it started with a force of 0 and then it gets to another force. The force is not constant. So we need to use an average force. Initial force plus final force divided by 2. Or simply half F, because initial force is 0. Final force can have a value we can call F. 0 plus F divided by 2 give us the average. And 0 plus F divided by 2 is simply F over 2 or half F, which is the average force. Now times the distance, which is extension. That will give us half F times E. So that's the average work or the work done in a string, where F is the force, E is the extension. So half times force times the extension, which is basically area under the graph. Area under the graph of force against extension will give us the work done in stretching a spring or deforming a spring, or the energy stored in a spring that is stretched or squashed. That work done or energy is half times force times extension. Now we can take that further by, if we take that further, we'll be able to get this equation half Ke squared. Now how did we get that? We know that from Hooke's law, F is equal to Ke. You know, Hooke's law is F equal to Ke. Or F equal to Kx. K is the spring constant, E is the extension. So if F is equal to KE from Hooke's law, and then we substitute KE for F, instead of F we substitute it with KE, the equation will change to half KE squared. What I mean is, for this F, we change this F to KE. This F is now substituted with KE. So instead of half FE, we're now going to have half KE for F times E again. So half KE then E, or half KE times E, which will give us half KE squared. So the energy stored in a spring or in a string is half KE squared in terms of the spring constant, or half Fe squared, or half Fe in terms of the force and the extension, which is equal to half Ke squared in terms of the spring constant K, and of course the extension. Now we can look at different ways we can analyze the spring constant. You know, a string can be connected in parallel or in series. This is what I mean. I'm going to draw a line here. Anyway, this is about a different topic which we'll look at later in another lesson. But for now, we're looking at stress and strain, or deformation of solids. Now, a string can be connected in series like this. I mean, you can have two strings in series. This is one string, then yet another string. I'm going to add this other string in green. So let me call the first string A, having a spring constant of K, and then I'm going to call the second string B, having a spring constant of B, or KB. The first string has a spring constant of Ka, the one in red. The second string has a spring constant of Kb, the one in green, connected in series. That's end to end. This is series. Or end to end, one end to another end. When strings are connected in series like this, the total spring constant, this total spring constant K total, is equal to 1 over a spring constant of 1 plus, actually this is how we should look at it. If you remember resistances connected in series and in parallel, it will give you an idea of what we're talking about, though in a reverse way. So 1 over the total spring constant, I'll call it 1 over K total, is equal to 1 over K1, that's Ka, plus 1 over Kb, 1 over Kb. You can recall where we normally do this in electricity. In fact, in electricity, you find this for parallel circuits. Incidentally, when strings are connected in series, this is how we find the total spring constant, which is like what we do when resistors are connected in parallel. In fact, this will give us product over sum. If you have only two springs, for only two springs, this is going to be product over sum. So that's for only two springs. If you have more than two, you have to apply this formula as it is. 1 over K total is equal to 1 over Ka. That's for one spring, plus 1 over Kb for the other spring, plus 1 over Kc for the other third spring, 1 over Kd for the fourth spring, as many strings as possible. But for only two springs, which I'm going to talk about now, for only two springs, for two springs in series, we can simply do product over sum. K total, this total spring constant is simply product divided by sum. Product divided by sum. In other words, the product of the spring constant divided by the sum of it, which in this case will be Ka times Kb over Ka plus Kb. Let me write it out in full. And that is only when we have two springs in place. So this will be Ka times Kb, Ka times Kb, or Ka-Kb divided by, okay, I think I would better use just the same color. Or, okay, let's go ahead with Ka times Kb divided by Ka plus Kb. Ka times Kb divided by slash Ka plus Kb. Okay, so Ka plus Kb. Ka, I think I zoom this thing to 200% to reveal it better. As for string in series, Ka plus Kb plus Kb that's product over sum in brackets. Let me write it better so that this will come out clearer. I said for two springs in series, the total spring constant, K total, is simply product over sum. That's only for two springs in series, which in this case is going to be Ka times Kb divided by Ka plus Kb. Plus Kb. Okay, that comes out better now. So plus with our bracket in place. All right, so that's what we do for springs in series. And if you notice, when springs are connected in series, the total spring constant will always be smaller than the smallest of the spring constants. You can use an example to illustrate this. Assuming just for your own illustration, you can use a spring constant of, say, 5 Newton per meter for Ka, and then the other one maybe 10 Newton per meter. By the time you calculate the total spring constant, which is Kt, whether you want to use this formula or you want to use this formula, product over sum, which is Ka Kb times Ka times Kb divided by Ka plus Kb, you will discover that the total spring constant, the total spring constant will always be smaller than any of the smallest, or it will be smaller than even the smallest spring constant. In other words, the spring will become less stiff. When you connect springs in series, it becomes less stiff because the spring constant gives an idea of the stiffness. The bigger the spring constant, the stiffer the spring. So if the total spring constant is going to be even smaller than the smallest one, it means that springs connected in series will produce a less stiff total spring, or less stiff effect, because the total spring constant will be smaller than even the individual spring constant, or the smallest of them. That's for spring connected in series. Spring connected in series, that's end to end. Now, springs can be connected in parallel. Let's illustrate that here. We can have springs connected in parallel. This one is easier, so we don't have much to do. The springs are connected in parallel like this. We have this first spring in red connected like this, and then another spring in green connected like this. In this case, they are connected in parallel, all supporting a load, both of them holding a load in place. The spring constant of this one is Ka, the one in red. The spring constant of the one in green is Kb. When connected in parallel like this, that's across each other, not end to end like in series. This is for parallel. Parallel is different from series. Parallel is this way, series is this way. Series is this way, parallel is this way. Series, they are connected end to end. One connected from the end of the other. This green one connected from the end of the red one. That's series, end to end. The parallel is across each other. The total spring constant for parallel, K total, is just the sum of each of them. So that would be Ka plus Kb. a simple sum. And we can see that the total spring constant for springs connected in parallel, the total spring constant will be bigger than even the individual spring, because you have to add up the individual spring constant. So when springs are connected in parallel, the system becomes stiffer because it's a higher total spring constant. So in this case, system becomes stiffer. Higher K means or implies stiffer system. Means stiffer. If K is higher, if the spring constant is higher, it means it is going to be stiffer. But here the spring constant is less, it's going to be less stiff. So this one is lower K, or I can call it lower K total, for lower K total, which implies less stiff. That's for series. Lower K total for series will be less stiff when in series. Higher K total for parallel, that means more stiff or stiffer. So this is the way it will be when these springs are connected in this way. In summary, in series end to end, the total spring constant is 1 over K total equal to 1 over Ka plus 1 over Kb plus 1 over Kc plus 1 over Kd, as the case may be. Or when there are only two springs, the total spring constant is simply product over sum, or Ka times Kb all over Ka plus Kb. That's for series. And that will produce a lower total spring constant, which means less stiff. But in parallel, for parallel, the total spring constant Kt is just the sum of the individual spring constant, and that will make it stiffer. So when they are arranged across each other, which is parallel, it will produce a stiffer system.
Please don't forget to like, subscribe, and comment. Thank you so much.
Welcome to Like Learning School, your premier online education platform. At Like Learning School, we are dedicated to helping students and learners unlock their full potential, providing them with the foundation, support, and guidance they need for academic excellence. Our platform caters to two main target audiences. Firstly, we work with school children of all ages, offering academic follow-up and accountability partnerships. Our seasoned tutors provide personalized attention to ensure students stay on track and reach their goals. Secondly, we support students and learners who are preparing for internal, external, entrance, or professional examinations. We offer comprehensive and well-structured support to help them achieve outstanding performance in their exams. Our robust virtual courses are designed to keep students engaged and motivated. With interactive videos showcasing our teaching sessions, students actively participate in the learning process, making education enjoyable and effective. But that's not all. We believe in personalized education. Our students have access to personalized tutorial sessions, whether online, physical, or hybrid, tailored to their unique learning needs. Join us at Like Learning School and experience a transformative education journey. Visit our website at www.likelearningschool.com or contact us at +234 808 509 5144 to learn more and get started today.